भैया on YouTube live. Hello,
Hello.
am I audible?
Yes.
Okay, so let's start or should we wait? So hello,
Hello.
yeah. So okay, we are starting. So very first, I am just giving you the context that here we are seeing the COMSOL tutorial for the Metasurface purpose only. So in which I will show you the example from the paper which I am showing here. Okay, let me switch the tab. So can you see the screen?
Yes, भैया.
Hello.
Yes, we can see.
Okay.
Yes, भैया, दिख रहा है.
Okay. So I will here I will take the example from this paper. So in this paper we make this shape of the metasurface, which is membrane metasurface, and then we will calculate the eigen mode frequency like something like this. So all the modes we can calculate in the metasurface mode we can calculate with eigen frequency analysis, and then later I will show you how to calculate the transition, something like in this figure. If you see this blue curve, right, so this is the resonance, metasurface resonance you can simulate in the COMSOL. So here it is LCP and RCP transition, but I will show you the linear transition calculation, and then you can extend it to the circularly polarized light and left and right circularly polarized light. Okay, so very first let's come to the COMSOL. Okay, so here there are, this is the interface of this COMSOL. So very first I will start just like when you open the this one, so it will open from this window. So from here you can go from model wizard or blank model. Okay, so in blank model, if you click, then this will be nothing in this model, so you have to add one by one the step. Okay, and if you go with the model wizard, so it will ask you first like in which dimension you want to do the simulation. For example, if you want to do simulation in 3 dimension, or you can make your geometry in 2D as well, like for example grating and all these things you can do in 2 dimensional as well. And if you have some structure which has axis symmetry, then you can also choose 2D axis symmetry dimension space as well. So here I will show you first the 3 dimensional metasurface we will make in that one. So I will select 3 dimensional space, and then after you have to choose the which physics you want to use. So here in this one we are using optics module, and in optics there is a wave optics, and inside the wave optics you can see there are 2 3 other module, which is called electromagnetic wave beam envelope method, and electromagnetic wave boundary elements, electromagnetic wave frequency domain EWFT, and electromagnetic wave time explicit and transit, and FEM BM. So I will show you here using electromagnetic wave frequency domain, but if you are doing simulation with long waveguides, then you can also use EWBE. So only the now forming of meshing and some calculation algorithm is changed in between this EWBE and EWFT. Okay, so I will choose here EWFT for this tutorial, and then after that you have selected this physics and physics interface, and after that you have to go to this study tab. Okay, so in this study tab there are options like eigen frequencies, frequency domain, adaptive frequencies sweep, boundary mode analysis, frequency domain model, and frequency domain source sweep, and wavelength domain. So basically this eigen frequency will calculate the exact resonance frequency of your metasurface, and then if you want to do the transition calculation, then you should choose frequency domain. And other than boundary mode analysis and all these things, when we are calculating with some other purpose, then I will show you in later tutorial that where to use this boundary mode analysis. So wavelength domain and frequency domain are related. Only the difference is in frequency domain you have to choose the frequency, like when you sweep the spectrum, then you have to give the in the frequency, and if you want to give in the terms of wavelength, then you have to choose this wavelength domain. So these are very similar, only just change of like frequency to wavelength, that's it. So like if you go through this process, then this much interface will open. So here you can see very first, like if you go to one by one, first is global definitions, then components and study and results. These are four uh, steps for the simulation. So very first, if you open global definition, then you will see the parameters. Okay, so in this tab you have to, you can put all parameters you are using for your simulations. For example, for my meta surface, what we need periodicity. Okay, and then if you see in our structure, so let me show you. So if you see this structure here, can you see this? So here we need periodicity, and then equation of this parametric curve is r0 plus rd cos 4 phi. Okay, so we also need r0 value, rd value, and then the height of the membrane film. So we need all these things. Okay, so all these parameters you can put in this parameter. So for example, I am putting this periodicity as a p. So we can put periodicity as a p for 1 micron here. For example, in this paper also I use 1 micron, and then I choose r0, which is 0.35 times periodicity, and then I will put rd, which is 0.15 times p. So okay, this p is not defined. Okay, so can you see this p? If I put this one, and whatever unit you will put in this square bracket, that it will take automatically. So if you want to take in nanometer, then you can also write nm, then it will come around 1 into 10 power minus 9 meter. Okay, so this is all the units are inbuilt in this one. In this form you can uh, give this unit in the square bracket only. So you can also can put some description for your further uh, so that you did not forget that. Like for example, I will put here periodicity for my metasurface, and then r0 is some radius, and then I will put rd, that is distorted radius. Okay, then what else parameter we need? So we also need the thickness of the membrane, so I will put this h. And in this spectrum I took, like in this paper I took around 500 nanometer, so I will put 500 nanometer of thickness. And then one important thing to remember, that if you are using this FDTD or numerical simulation, so in that one all the domain which you are not defined is considered as a air, but in COMSOL this air domain you have to also define. Okay, so here I am taking this uh, height of the air and substrate, all these medium, we have to define some parameter. I will put h here, and this will, like you can take up to whatever your interest of wavelength. So this thickness of substrate or thickness of air, you can take up to half, greater than half of that your wavelength, so that some diffraction effect will not uh, show in your simulation. So for that purpose I am taking around 1 micron of h here. Okay, and then also you have to define some PML domain. So in PML domain I will also take one parameter HPML, so that I will take around 500 nanometer for here, and that can vary up to your if you have very small wavelength, you can change this very small. if you, so it all these parameters, background parameters I took usually compared to the wavelength. Okay, so all these initial parameters I have defined here, and then we will go to your geometry part, very first part, to make the geometry whatever you want. So for that purpose you will make geometry from here. So like in global, all these parameter you can define, and some other options, like if you want to define some global variables, you can also define with using this tab. And if you want to define some functions which can be used globally, like in all uh, in full model, then you can define these variables and functions, all is under the global definition. Okay, so and also you can define some geometry if you want to change the geometry in the simulation, then you can define all the geometry in the global using this tab. Okay, so this parameter variable, and this is the option for function. So you can define various function, analytic function, interpolation. If you have some refractive index in form of table, then you can import here as an interpolation function. And okay, so the next step, you should define the geometry. So for that purpose you should go here, the component option, and in this component option you will find the geometry to tab. Okay, in this geometry tab you will click, when you click in the uh, right click in this on this one, then you will find all the basic blocks of the geometry, for example block, cone, cylinder, sphere, and some primitive you can define, so that you can define according to your need. You can use all these uh, tabs. So for example, so very first, my first aim to define the full domain in which our simulation will be done. So for example, if you have, if I take a block, so this will be a cuboid form. So in this one, since our metasurface, in metasurface we will simulate only one unit cell, so we will give the width and depth equal to our periodicity, and in our height, so that will be the total height. Like, so here there are different ways to make a geometry. So some people prefer that block by block, so they define each block for each domain. For example, one block for substrate, one block for ER, and then one block for your metasurface. What I usually do, I make only one block, and then there is one option in the layers. So here you can divide your full block in different domains. Okay, so for example I am showing here, so the total height will be, our total height will be like, uh, downside there will be substrate, and upper side there will be air. So I will take the same height for both sides. So I will take 2 times h air which I defined in the parameter. Okay, and then both side will be PML, so I will take 2 times of h PML. Okay, and then I will also add our metasurface thickness in this one. So this is the H, capital H. So when you click here from build selected, so you can see here one block, one single block in this one. Now if you go to the layer, so in how to divide this full block in our different domain, so there is options, layer positions. So if you put from bottom, then you have to define each domain thickness here. From the bottom you can calculate. Okay, so for example, if I put some very at the bottom, because I am take here from the bottom, so it will be h, so very first it will come HPML. So if you build selected, then this domain will be divided. Okay, one domain and two domain, so this will be your PML region. And then second one will be your substrate. which is equal to our h air thickness, then you can put this one. Okay, and in the third layer will be our metasurface, which thickness is h, then you can give h, then this is our metasurface thickness h, and in the last part again this there will be one h air, so this will be your, and the last domain it will remains, that will be our PML in the upper side or air side. Okay, so this is the uh, full way to make a different domains in the same block using the layer option. Okay, and in the second way you can also choose from bottom and top both side and then give only one thickness, then it will divide from both side, top and bottom the same thickness. Okay, so this is the block, and then in the next step I will make our meta surface. Okay, so for that like you can, so then there is also some option in the graphics, like for example you cannot see inside in this box, so you can use the transparency option, which is you will find here. Okay, so this is your transparency, and then you can see what is inside. Okay, and then if you want to fully transparent, then you can choose this option as well. And then like for example if you have something like uh, uneven meta surface, something like that, and then you want to align the axis, then you can tap, click on this tab, this button, like go to a default view, then it will becomes like that. Okay, so this is these are some graphical options in the graphic window. And in the next step I will make the unit cell. So in the unit cell you can see in my paper uh, this is some shape which can be defined with the parametric equation. Okay, but you can, if you have very simple design which can be made by ellipse or circle, you can make using that as well. For then, so I usually prefer to make the unit cell using work plane. So the work plane is it will define you a work plane 2D, and then in two dimensional you can sketch your whatever unit cell is, and then you can extrude it to your height of your metasurface thickness. So this work plane, if you click on this one, you can see one uh, this is 0. Okay, okay, so one more thing, in the block here is the option which is called position. So it is choose base as a corner. Okay, so it will start x comma y comma z from 0 comma 0, and then whatever thickness you will give, so this point is 0 comma 0, but I will prefer with the center one. So then the center of this block will be 0 comma 0 comma 0. Okay, then because then you will exactly know where is your work plane. So it is your work plane, but our meta surface will start from somewhere here. So meta surface midpoint will be also at the origin. That is the advantage if you choose the position of this block as a center. Okay, then the z coordinate of your work plane should be from which your meta surface will start. So that will be minus h divided by 2, because full height of your our meta surface is capital H. Then this will start from minus h by 2 to plus h by 2. That's why I will give this work plane coordinate from minus h by 2. So next I will give this plane geometry. So now only our two-dimensional plane is showing to us. So if you want to make, for example, so in this work plane there is also plane geometry. Okay, so whatever geometry I will make in this one, it will comes when you right click on the plane geometry. So when you right click on the plane geometry, then you will see circle, ellipse, rectangle, square, and then again primitives like circular arc, and whatever you want to use you can use. Like for example, if I want to make only circles inside, then you can make, click on the circle and then give the radius, for example r0, and then will select it, so this circle will form. And then after, when you right click on the work plane, and click on the extrude, and then in the extrude there is one option, like for example extrude from work plane. So which plane you want to extrude. So here I select, I have only one plane, so only one plane is coming. If you have more than one plane, then all option will you will see here. And then how much height you want to extrude. So this extrude height will be equal to our metasurface thickness in our case. Then if you will select, so you can see this circular cylinder formed here. Okay, then this is one way to make only the circle. And then if you want to make some other geometry, you can use any combination of all these circle, ellipse and rectangle etc. But in the current example, as I am showing you a geometry which is formed using parametric equation. So for that purpose, and also I will mention here that in our paper whatever I do, we are using membrane metasurface. In that, the full area is membrane and only the shape which is parametric equation, that is the hole inside the membrane. Okay, so for that purpose I first make a full area as a membrane, so that will be our as a rectangle I can add. So this will also go from the corner at 0 comma 0. So I will also change this position from corner to center, and then I will click on build selected. Then you can see it is coming on our plane boundary. Okay, and then in the second step, then you will choose more primitives. Inside more primitives you will find the parametric curve here. Okay, so in this parametric curve, this s is your parametric variable. So in our case it is from minus pi to pi I am using, and then our equation is something like r0 plus rd times cos 4s. So it will be in this is equal to r. So in Cartesian coordinate, this is r cos theta is x. That's why I'm using this. And then I will copy and then paste again. And then in this pi section is just r sine s, right? Sorry, sine theta. Then if you click on build selected, then you can see here this parametric curve is formed. You should remember that if you are making the geometry using parametric curve, so this equation is giving only the curve, not the domain you want like full inside that. Okay, so to convert this curve into the domain, you have to right click on this one, and then there is option for conversion. Okay, so in this conversion there is option which is convert to the solid. So when you choose this one, then you have to, so in every node you can see there is an option of label. So you can label is according to your convenience whatever you called it. Okay, and then there is an input object. So in input object uh, we will give this curve. So you can see this is only curve, not the solid. But once you use this convert to the solid and then build all, then you can see this full region can be selected as a domain, and this is your membrane and this is your whole area which I will subtract from this region. And then if you want to rotate all these things, like parametric curve is rotated by 22.5 degree in our paper, so I am just taking that one. So this is the geometry. And then again, since I want a hole instead of this domain, then I will go here, and then there is an option called Boolean partition, and then you can take a difference from here. So then for add I am using this tab, and then whatever you want to subtract in that one you can choose in this option. So for that, if you see here, this is now active, and whatever you select here, that will come here. Okay, and then when you want to select what to add, then you have to active this one, change from here, and then click on this one, and then if you click build selected, then you can see this area is subtracted from the whole membrane. And then if you want to, if you go to the extrude, so I have already given the thickness of this extrude, and then if you click on build selected, you will find nice geometry here, you can see. Okay, so this is the geometry is formed. uh, so this area, so here I am not using the substrate. Okay, so both side is here because membrane is freestanding membrane. But if you want to make the lower part as a substrate, then you can use the node in geometry, and in the geometry there is an option, the partition object. Okay, so if you select this partition object, and then what object you want to partition, so this is the full domain, because initially I did not I did not do the partition at the place of substrate. Okay, so I will select this domain, and then I will take a tool object. So this tool object from which I want to partition, that will be our work plane from which our meta surface is started. Okay, so then if you build select, now if you see, after this partition, this lower domain will be separated from the upper domain. Then lower domain can be used as a substrate, and upper domain can be used as a work plane. Okay, sorry, for the air purpose. So this is the geometry, all geometry is formed. Then
Uh,
yeah,
Sorry, I have a question. Can you also define like another work plane below the
yes,
this meta surface plane and then make that the substrate? Like extrude that and make a substrate. Is that possible?
yeah, that is also possible, but that will be only extra things. Otherwise, this part will be as a substrate you can use, but you can add as many as you want work planes, and then extrude uh, means individually each work plane.
Okay.
Okay,
Okay, thank you.
and the next one is, then once the geometry is formed, next you will choose a material. So then you can see after geometry, this is called material. So in this material section, if you already have selected the physics, then it will already ask whatever the physics wants in the material property, refractive index, or permittivity, or some other model you want to use. Anything you can use here. So first I will uh, browse. You can go right click on the material and then click on the browse material, and when you browse this material, then there is all materials in different category. Whatever you want, you can select it. But very first, there is a built-in material. The air is already you will find in the built-in at first column. Then you can add this air by double click on the air, and then click on the done. So for now, all the domain is selected as a air. Okay, and if you see inside the air, the right ticks are on refractive index of real part and refractive index of imaginary part and real part of refractive index. Why only these two are clicked and all other are disabled? Because if you go in the physics section, and then if you go in the wave electrification section node, then you will see here electric displacement field. There is choose electric displacement field model is as a refractive index. Okay, for example, if I change it to the relative permittivity, then you will need relative permittivity and relative permeability, and as well as the electrical conductivity, and all you should choose from material. Okay, so whatever in material. And now if you click on the air, then you can see now it needs relative permittivity, relative permeability, and electric conductivity. Okay, so whatever parameter is ticked as a blue means, so they are already is defined in the wave electric equation, whatever you model you are using. Okay, so for safer side I am choosing a refractive index again, and then you can see in the air again this refractive index and refractive index is coming. Okay, if you are not selected till now the physics, then there is nothing will come, and then you have to choose from the material property what property you want. Okay, so always choose physics first and then you go to the material. That will be easy for you if you are new or beginner in the COMSOL. So in the next section, uh, the second material, whatever our membrane material, so I will add this as a blank material. uh, I am choose, and then after that, if you when you add this material, you can see there is nothing material properties coming, but as soon as you select this part, this will show refractive index real part, and this will be red. And if you give here some value QRT of 12, I am taking the silicon, so just I have put square root of 12 as a refractive index. Okay, so this is the refractive index I choose because this is constant value I choose in the paper as well. But if you want to choose some other materials which you have, so you can choose that from here. Like if you go to the bronze material here, and then you go to the like any materials property you can use. So you can choose here optical. Inside the optical there are lots of material here. So in inorganic there will be a silicon. So here is the silicon, and then you can go crystalline silicon or amorphous silicon, whatever you want. What And then you can, but always remember that in when you're choosing this, so each model has in particular range of wavelength. For example, it is from 0.21 to 0.83. So choose a model which falls in your wavelength spectrum range you want to do the simulation. Okay, so this is the important point here. And then if you once you select let's say this model, which model you should choose. Okay, I will choose this one for the example. 293, this is the room temperature silicon refractive index from 1.2 to 14 micron. So maybe this is not for our use because make I want to use this simulation at 1 micron, but the refractive index is from 1.2 micron. Okay, so I will choose some other model which is range from yeah. So okay, I will choose this green silicon model, and then if you choose this one, then you can see there is called this is written some function here. Okay, so how it works I will just explain little bit here. So this is the basic, and then if you expand this refractive index, you can see there are two interpolation function is defined. Okay, so inside this interpolation function you can put your table as well, whatever you have in your unknown material or some new material as well. But this will looks like this, like first basic, some basic, and then refractive index. Inside the refractive index, two interpolation function. One is for a real part of refractive index, second part is imaginary part of refractive index. Okay, and then how can we use this function? So whatever function name you should give here as a function name. For example, it is given an I and it is given an R. Okay, and then interpolation you can just choose here, and then in the argument you have to choose like what is your x-axis. In x-axis, if you are wavelength in nanometer, then you should choose this unit as a nanometer, and if you have x-axis as a frequency, then you have to choose as a hertz or terahertz or whatever you want. And then you can also check using the plot tab here. So if you plot it here, the whatever refractive index value is given in this table, it will show here. So this is your refractive index function you are using in your material section. So this is these are options if you have the refractive index as your for example, if you have measured refractive index from ellipsometry, you can put that table in this function, interpolation function. Okay, so for now I am just deleting it because I am using the constant refractive index as silicon standards square root of 12. Okay, so and one more thing, like whatever like I have chosen here for all the medium. Okay, but once you have choose another material after that and you have selected something, then it will override your previous material. Okay, so you don't worry about that. You should not choose the material in the air section or something. Whatever you choose in the last material in that domain, that will override the previous one. For example, if you go into the air, so this third section you have written here as a overridden, so it is overridden, so it will not considered as a air now, it will be considered as a silicon now only. Okay, so this is one thing to notice here. And then now comes to the physics, how to set the physics. Okay, so in the if you go to the electromagnetic wave frequency domain, so you will see here, you can see the equation, what equation it is going to solve here, but there is no use for now. You cannot change something, you can change, but if you have chosen different study, you can change here whatever you have, but uh, uh, better not to touch here until you don't know about all the things. So next thing, this full field. So here I would like to mention that there are two formulation that the COMSOL can use. One is full field. So in the full field, uh, it calculate the full field using the Maxwell equations, and uh, like and the second formulation is scattered field. So in that one, uh, how it works, like whatever background wave type you will give here, so it will consider the light is coming on your metasurface, and then it calculate the scattered field only. Okay, using that background field. So this is the meaning of this scattered field model. Okay, so here you can use linearly polarized light, you can use Gaussian beam. For example, you are exciting your metasurface using Gaussian beam, and then some scattered field will come out from your metasurface, so it will calculate all the scattered field, and then you can do the calculation according to your convenience, whatever you want. So but in this tutorial I will use this full field, but I am just want to show that there is one other option as a scattering field model you can use here using this one. So here it is a full field and nothing else you should touch in this section. Then second option is wave electric equation. So there is the default wave electric equation, so you should not touch this setting as well until you need this electric displacement field model have to change. Like for example, you don't know the refractive index of the material, you have some Selimar dispersion model or something, then what you can do, you can just right click on your electromagnetic wave frequency domain and then add one more wave electric equation. So all these three is by default, and then if you add this one, and then you just select the domain in which you don't know the refractive index. For example, I don't know the refractive index of silicon nitride, no, sorry, silicon, or this domain. Then once you have selected this one using new wave electric equation, whatever you add in this one, Then again you can go electric displacement field model, and then you can select relative permeability or whatever model you have. For example, if you have Drude Lorentz dispersion model for this section, then you can select this one, and in that one you can directly define all the parameters of Lorentz model here as well. Either you can just select from material and then add one extra material in the material section. Otherwise you can also select also put all these value here as well. Okay, so this is the another way to add
I have a
some
question.
material. Okay.
Sorry. So what is the difference in choosing the material in the material tab and or defining it here? Can you not do it there itself?
uh, so uh, I will, so that's why I told you that in material section, if you have, okay, so if you add some material section, then in this wave electric equation, whatever electric displacement field model is here, so it will apply all the materials. Okay, you are selecting in the material. But if you want to add some extra material, for example, you have in your model you have 4 different materials. Okay, and then for 3 materials you have refractive index. Okay, then in one material you have permittivity, not refractive index, and for the one material you have Drude model, and then for the fourth material you have Shalimar dispersion model. Okay, so you have
Okay.
4 different material and 4 different model. Then you have to choose this wave electric equation for the first model as a Drude model, and then add one more wave equation electric for the
Okay.
different model. So this is the difference between you are choosing material here or here. So
Okay.
whatever, so you can add all the materials here, material 1, material 2, material 3, and you can select in the material property whatever material property you have. Okay, then you have to choose wave equation electric model for that particular domain and choose that particular model you have in this
Mm.
setting section. Okay, for
Okay.
example, if you have Drude model, then if you are using, so either you choose all 4 material there, or if you don't want to choose all the materials here, then you can directly put the values as a user defined here only. Okay, that will work as the same actually,
Mm.
but this is just an option for if you have different model for different material.
Okay. I understand. Thank you.
Okay, so uh, for this tutorial I don't need different models because for the silicon I am using just a factor index, but that is for just for option you if you need in future. Then if you then the second step, like once you have defined the materials, then you need to do the periodic boundary condition. Okay, because this is metasurface, and the you have to choose different periodic boundary condition in different direction. So that will also you will find here there is a periodic conditions. So periodic condition, when you select, there is will be option type of periodicity. Okay, so the type of periodicity, so here is the if you see here, this is the XYZ direction. So this periodic boundary condition, we have to choose 2 periodic boundary condition, because one periodic boundary condition is in one direction only, for one direction. So then you have to select these boundaries like this, and then just move it like this. So how to move this one? So just left click on the mouse, and then you can move the mouse, then it will move like that. Okay, then next will be, and then you can choose different type of periodicity like anti periodicity, and Floquet boundary condition, cyclic symmetry, or continuity. Basically, in our metasurface, we use Floquet boundary condition or continuity. Continuity is true if you only want the reflection and transition in normal incidence. If you want some oblique incidence, then you can also choose Floquet boundary condition. Okay, so in this tutorial I will calculate only for normal incidence, so I will just put it as a continuity. And then the second boundary condition you just duplicate, or you can add from that one. And then if you duplicate, then first remove the previous one and add in the other direction. Okay, so this is the so you can also check, like if you remove the transparency here first, then some other boundary should not be chosen. Only this boundary and this boundary, all the boundaries should be chosen. And then second one in the y direction, so this is in this direction, and this boundary condition in that direction. You can name this if you don't want to confuse, like x periodic, and this is our y periodic.
Can you choose both of them like in the same?
No,
Okay.
because if you are choosing the periodic boundary condition, so
Yeah.
at the one periodic boundary condition will be extend the your metasurface in one direction, for example in x direction. Then the second boundary condition will extend your metasurface in y direction.
Mhm.
Okay,
Okay.
so if you want like only 1D periodic boundary condition, then in the y direction you just choose scattering boundary condition or some other boundary condition, and one direction is just a periodic boundary condition. Just like some people then use this nano beam structure in waveguide, there is a periodic hole in one direction only, so that then only choose one periodic boundary condition. Okay,
Okay.
so once your periodic boundary condition are set, next you should choose the source, or source is here like port source you can use here. Okay, so now comes to like what to study, and according to that you should choose. For example, in first example I am just calculating the eigen frequencies of this metasurface around our region of interest wavelength. Okay, so and then comes to the mass. I will come again on this section. So next it is the mass section. So if you have chosen the study already, so this mass will work as a physics controlled mass, and if you build this, it will build automatically actually. Okay, so if you are using physics controlled mass, it is good, you don't need to touch anything. But if you want to see what is happening inside the mesh, you just switch to the user controlled mesh, and then if you see, first they are defining the size for all geometry, then some particular geometry, some particular domain where the refractive index changes, and then some boundary size elements, and then they are using identical mesh because periodic boundary condition is happening. So whatever mesh on this face will be copied on this face. Okay, and then second identical mesh on this periodic boundary, and that copy to the that boundary condition, and the remaining is free tetrahedral mesh. Okay, but where is the PML part went? Because these upper two lower domain and upper domain we are using as a PML. So PML we use because like this is one type of open boundary condition in this PML. So whatever light coming on that surface, PML surface, that will decay inside that domain. It will not reflect back, because if it reflect back, then it will generate second or third order excitation and all these things. So prevent to that one, we use open bond deconduction PML. But where to find? So for that one, again we have option component. When you expand these components, then you will find before the geometry the definition. Okay, so inside the definition also very, like there are many things inside that. You can use variables, functions for this one, and non-local coupling. Like for example, after simulation you need some integration over some domain or some surface, you can define that one, that coupling. Like for example, if I define the integration over our meta surface, so you just click on the integration and then click on that domain, in which domain you want to integrate. Then in the next step you have to define the operator name. So here the operator name is int op. Okay, you can define as anything like int meta surface integration, integrating over meta surface. And then if you want the surface integral, you should define as a boundary here. For example, on this boundary you are integrating, or this boundary you are integrating, like that. And if you are defining the line integral, you should define edge, for example along this edge or along this edge. Okay, you are seeing my cursor, right? Okay, then but if you want volume integration, you should define as a domain, like for example I am defining here. Okay, then defining all these integration, so there are many options you can see here. Coupling, integration, average, maximum, minimum, whatever you want you can define. And then there is also option in the same tab under definition, the perfectly matched layer. So in this perfectly matched layer, you just click on that one. Now it is coming under the artificial domain. Okay, so this perfect matched layer, you can just define the two domains whatever you want perfectly matched layer. So these two domain will work as a perfectly matched layer. So that will be shown the domain number here. Okay, 1 and 5. Okay, okay, so now I have defined the integration, for example. And then if you want to use some integration formula, then you can just define the variable here. For example, I want to calculate the electric field integration inside your meta surface. Then you just do the uh, in any variable name, and then use whatever the function name here, int meta. So I will just define int meta, and then inside one you can define the variable. So in the variable in this model will be according to your whatever, like if you are choosing here electric waves frequency domain, so the function is EWFD, right here. So you can also change the name here, EWFD, you can change it, otherwise keep it standard EWFD. And then you just define any variable. For example, if you want to integrate electric field X component, so you should named as EWFD as a prefix dot EX. Okay, you can see unit will coming volt meter square, because EX is uh, volt per meter and it is integrating over volume, so unit will come here. And if unit will mismatch, it will turn as a yellow. And if it is wrong, why there is some thing which is not defined or some severe wrong thing, then it will appears as a wrong red one. Like for example, if I int sorry if I write int surface, and if I define some random thing like EX, So Ex is already defined as a bolt per meter. So for example, I will define Bm. Maybe this will not anything. So you can see here some yellow thing. If you keep the cursor here, it will showing you unknown variable Bm. So this is some way you can see like what error is happening in our thing. Okay, keep this in mind. So like that you can define these variables. Okay, now if you, since before I did not define the PML, that's why this meshing is happens like that. So I will go again and choose as a physics controlled mesh, and again click on build all. So this mesh, you can notice the difference. In the PML region there is a swift mesh. This is like swift mesh, because if you see again with the user controlled mesh, you will see size 1. Now it is coming distribution again, and mapped mesh, mapping, and then, so this is all the mesh tree it is forming. But you should not afraid of all these tree how it will build. You just use physics control mesh and build all, it will take care of that one. Okay, then the next thing is, okay, you can also add 2 or 3 study, but at a one time you can run only one study. Okay, so I will come step by step. First I will calculate the eigen frequency. Okay, so for that I will add one another study. So in that one I will choose this eigen frequency. Earlier I choose this wavelength domain, but the eigen frequency I will choose. And if you choose this eigen frequency, then it will ask you, so in the eigen frequency it will not it is not necessary to put any port, because eigen frequency is the way the Maxwell equation solution independent of the source. That's why I did not put any port in the physics section. I want to just calculate the eigen frequency of that one. So if you see here options, solver, so you don't touch, you should not touch the solver. If you have proper knowledge of all solver you can change, but until you don't have the, so default solver is best for us. Then desired number of eigen frequency, how much eigen frequency you want near that interest of your eigen frequency. So I will usually keep around 10, or you can choose bigger number and less number as well. So for example I will keep here only 6, whatever is default. And then you should choose like your approximate, like in which frequency around you want to search. For example, here the periodicity is 1 micron, and this structure is around near IR. So I will put this frequency as 1.5 micron around that region. Then if you click, so that these two things only you have to put, and then you just click on the compute. So it will start computing, and everything will be disabled. You cannot click anywhere until it runs. Only on this button to cancel it. Okay, so it is calculating. So then it will show the convergence plot as well. Okay, so that's it. So these eigen frequency, then how to read this eigen frequency, that is up to you in your results what you want to see. So the difference from the FDTD, here you don't need to put any specific monitor at some point or some other point. It is calculating electric field in every point in our domain. So whenever you want you can calculate integration or anything you can do for any quantity. So for example, So this is the eigenfrequency I will get. So I choose 6. So this, okay, now I will explain again. So till now, before the simulation, I explain you about components. In that the definition comes, the physics part comes, material parts come, and geometry part come. Okay, then after setting all the physics, you went you went to the study. We went to the study. We do the study as eigenfrequency, and now the results has come. So now we will go to the result section in this one, and in the result section, if you right click on this one, you will find different type of plots here. So whatever you want, you can select it. So I will select 1D, for example, and some default plots will come. For example, electric field, this is actually 3D plot. If sometimes it didn't come, how to make this node, I will show you. I will just delete it first. So how to make, how now you can see in the data set, this study 2 and solution 1, this is your all solution inside this one. But if you want to plot some specific plot, so for example, I want to see electric field for now, because eigenfrequency mostly will give you the eigenfrequency in the complex form, omega plus I gamma form, and then eigenvector. So eigenvector is just electric field. So you just do the 3D. In the 3D, if you right click on 3D, then it will different type of plots. So usually in the three-dimensional plot, which is by default comes, that is actually multi-slice, which is comes under more surface plots, that is the multi-slice. So when you put on the multi-slice, there is one expression node in the setting. So there is a norm E, and then you should choose the planes, number of planes, either number of planes or coordinate of the planes. So for example, I have chosen our meta surface at the center 0 comma 0. This now the benefit is your central plane is at 0 coordinate. Otherwise you have to calculate at which plane you should put that plane. That's why initially I put this as a center, not at the position as a corner. So, and I will block these by z and xz plane, and in the z plane I put the coordinate as a 0. Then I will put plot, and then you can see one curve is here. Then you can now in the graphic section, you can put xy, so it will come xy, and then you can remove the transparency, so it will be good color. And then if you want to remove these dimensions, you can just click on this section, and now it is showing that these three corners, each plane actually differentiating, so that can be also removed by this stamp object. Okay, so now this is a good electric field plot. So okay, so if you have done 2 or 3 study, inside one study only, if you do the parametric sweep and all these things, then there will be option of data set. Parametric curve data set will be different, and this data set, so you can change data set from here. Sometimes if you plot, it will be none, then if you none, then if you plot, then it will be blank. Then sometimes you will, okay, what happens, why it is curve is not coming. So you should check first data set is selected properly, then you should plot here, it will come. And then you can plot different quantities, just changing this expression. For example, if you want ez only, you can plot this. Okay, and e by or ez. Okay, so mostly I will show you this norm E, and since this is eigenfrequency analysis, so it is calculating only eigenfrequency. So you can see here, just below the data set, this eigenfrequency. Okay, so you can see I choose 6 eigenfrequency, right, to search. So it will be number of 6, 1 2 3 4 5 and 6. Okay, so if you change this one, you can click on these arrows. It is, if you keep the arrow on this one, it will show you the plot next eigenfrequency. So if you change this one, you will find that this electric field is changing. Okay, so what it is, so it is different resonance is happening in our metasurface at these eigenfrequencies. And if you see closely on this eigenfrequency, so you will see this 193 terahertz, and this is your radiative part. So the radiative part is not coming in these 3 eigenfrequencies. They may be bound state in continuum eigenfrequencies, or some very high Q in which the radiative loss is nearly zero. So the difference in BIC and very high Q mode is you can find by using the eigenfrequency uh, electric fields profile. So that can be seen like in this plot. I can also add some arrow plots. So I will add here arrow volume. So in this arrow volume, so the component is ex, eby and ez, and then you can form the grid. For example, in xy plane I will put around 25, and then y direction also 25 grid, and in z direction I want to saw only on this plane, so I will choose just coordinate and then 0. So 0 is the same plane. Then if you plot, so you can see here the arrow of electric field here, you can see here, right? So the electric field dimension in z direction only. So this is probably a BIC mode here, and I can comment on this one by seeing the electric field, because this is C4 symmetry, and then if you drag the eigenfrequency like BIC as that one, so if you rotate this, the electric field will not change. Like if I rotate this, you can rotate this from here. Okay, and then if you rotate 90 degree, you cannot see the change. Okay, so that is the symmetry protected BIC actually. And then if you see, go to the next eigenfrequency, it is also a BIC eigenfrequency, and this one is also BIC, and this is the radiative. Okay, uh, one in C4 symmetry, one more identification is whatever the radiative mode will be, they will be degenerated. For example, I will show you here. So this eigenfrequency is 193, the second one is also 193, but they have two orthogonal electric fields. You can see this one and this one, they are just orthogonal to each other. So they are degenerate modes. So degenerate modes never can be a BIC mode. So that's why I can see here these two modes. So that's why, like, there are 3 BIC and 1 only radiative mode. So you can also increase the number of eigenfrequency here. For example, I will put here around 20, and now I will compute again, then I will show you some more eigen modes. So any question till now? I can give some answer of some doubts until this runs.
Can you explain variables once again, please?
Variables means okay.
While defining.
Okay, defining the variables. So here is the variables section. So for example, I am just uh, define only one variable like int b. Okay, for example, if you want to calculate something, I will show you when I am calculating the transition, defining some different parameters, or why not I should Okay, if you want to see the polarization in eigenfrequency, if I want to see like this mode for which polarization it will uh, couple. So for example, then you have to calculate uh, like let's see Cx coupling to the x parameter. So this is something uh, in the literature, if you find this can be done using the same thing. If you integrate this, the x field, and then one parameter, so coupling to the y, so I will just define b y. So if you define like this, then if Cx will be greater, then that mode will couple to the x polarized, and if Cy is greater than Cx for some mode, then it will couple to the bi mode. Or you can just define some linear dichroism. You will say linear dichroism that will be around absolute of Cx square minus absolute of Cy square. So this formula is only for demonstration purpose. This formula may be wrong, or okay. So I have defined here these variables Cx, Cy, and Ld. Okay. So what is your doubt? You can define any formula here.
With whatever variable or formula we define here, these are will be computed and will
Yeah,
reflect in the results, right?
yeah. That will be reflected in the results. Also, if you don't define here, then also you can uh, find it in the results. So that is one another way I will show you. So if you go to the study 2, so whatever last computation, it is 24 second. Okay, so after this written formula, I can also again compute. It will not take much time, maybe 30 second only. Okay, so now it is coming. If you see here, now it is the list of 20 eigenmodes. Okay, so in 20 eigenmodes, you can see 1, 2, these two are degenerate because 130, 176 and 176. Okay, now I want to see like the wavelength of these eigenmodes. Okay, then I will go to the 1D plot. In 1D plot, you can just choose this global. Okay, there is a line graph as well, point graph as well. In line graph, if you want to plot like electric field in the function of position, then you can plot this line graph. Otherwise, mostly I choose this global. Then in the global, there is this is y-axis data, you can see, and this is x-axis data. Okay, so on x-axis I want to plot the expression. Okay, you can solution number as well, because solution number will be first eigenfrequency, second eigenfrequency, third eigenfrequency, fourth eigenfrequency. That is the solution number 1 2 3. But I want exact the expression, what is the wavelength. So you can choose the parameter as expression, and then if you go, if you can left click on this one, this will be a replace expression, and this will be insert expression. So if you go to that one, then you will find all the quantity what it calculates. So if you go to the component one, because this is component one, if you notice there below this global definition, Then under the definition, whatever you defined, like for example the variable you defined, it is coming here exactly C, X, C, Y and LD. And if you are the by default inbuilt things, so it is coming electric magnetic wave frequency domain, inside that energy and power. And if you go to the global, the Q factor K0 and damping lambda 0. So if you want to see the lambda of all everything, so this is here. So I will choose the unit as a micrometer. Then in the y-axis I will plot exactly that LD I defined, that is the linear dichroism. So if you plot it, and this is coming as a line, so there is a coloring and style option inside that. In that one also you can just click none, and I will prefer as a marker because eigenfrequency is discrete thing, so I just okay. So if you see here, it is coming 0 line here, okay, or you can also plot 0 line. So this is the plot I found, okay. So using this LD, like that is the linear dichroism. So the linear dichroism formula, I choose Cx minus Cy. So if it is positive, that will be your X polarized mode, and the negative one will be your bipolarized mode, most probably, okay. That I will confirm when I will calculate the transmission. So you can see we found one eigen mode at 1.35 micrometer, 1.4 micrometer, 1.45 micrometer, and also everything, okay. Now, but whatever the degenerate mode, one mode will be bipolarized, one mode will be X polarized. So here this comes the wrong thing, like you cannot identify. So the exact formula is something you have to calculate eigenfrequency from upper excitation and lower excitation from both sides, okay. So okay, that will be later. If you want any, so if you have any confusion, you can ask me in person that how we identify the X polarized and bipolarized mode. But this is just example. If you give some variable, in variable some quantity, it can be plotted here as a function of anything you want. So I just want to see on x by x is the just raw frequency, and by x-axis the wavelength. So you can see 1.2. So I just want to see here eigen frequency of 176, the imaginary part at 1.2. So the Q factor is always based on this one, okay. Or you can do one thing. On x-axis I am plotting the wavelength, on y-axis I am just I will plot EW. So whatever expression you will write, you this prefix is necessary, EWFT dot. Then if you write Q factor, because I remembered most of the things, but if you don't remember which variable is which, so you just go here, and then electromagnetic wave frequency domain, in the global you have the Q factor, okay. So it is the same, EWFT dot Q factor, okay. And then if I plot it here, so whatever this 10 to power 7 and all these Q factor will not couple to your far field. So this is 10 to power 2, and this is something around 250 Q factor, okay. So I will show you the transition at this mode, which is 1.5466, okay. Now go how to calculate the transition. So this is the part here, the eigenfrequency analysis type of things you can do for your simulation, and you can find the initially what is the resonance frequency of your metasurface and all these things. And then if you change the parameters, like, okay, I will show you one more thing. Like now if you want to see, like if I change the thickness of your metasurface, how this eigenfrequency will change and anything, then you can go to this study 2. It is actually eigenfrequency I have done. So right click on that one, there is one option called parametric sweep. Okay, so if you parametric sweep on this one, then there is a parameter names. Then if you click on the plus sign, then it will go come all the parameters you define. So any parameter you define in your parameter section in global definition, that will appear here. And then you can sweep that parameter. For example, if you want to sweep the periodicity, sorry, so if you want to sweep the periodicity, you can choose this one, and then there is the parametric value list. You can choose the list from start to stop, or some random numbers you can also calculate, put like 100 micrometer. Always remember, whatever number you write, just mention the unit just after that, because sometimes you will not uh, notice. But if you just put 100 for example, okay, but this parameter default value in meter, then it will consider 100 meter. Okay, then you will see, oh, what happens, I am not seeing anything, very weird things will happen. Okay, so always remember to keep the unit in front of that one. This is a good practice actually. Like for example, then 2 micron or 3 micron. Okay, so okay, I will show you using only these two numbers. Otherwise you can give the long list inside this value. Then if you run now, so it should take around 1 minute, because for one parameter 24, then now two parameter will give you 24. Oh, something happens.
We selected 2000 microns,
Oh,
2 microns.
sorry. Mm, oh, sorry. This is very. You can see in the log what is happening, and in the progress also it will show the parametric sweep parameter piece value. For value 2 it is calculating for now, and in the next it will change. Now it is calculating for p equal to 3. is taking time. So any other doubt? Do you guys have any other doubt? Are you guys listening sincerely? Because you are asking no question. Eh? I am not seeing the screen of whoever is joining. Can you give the attendance? Who is there in the meeting? Okay, so this is completed now. So if you see now in the data set, so now there are two data set is coming. Okay, this is one is study 2 solution 1 and another is study 2 parametric solution. So this parametric solution contains whatever you parametric sweep you are doing, and the first one is the default one, which is without parametric sweep, whatever you do the absolute parameter in your global parameter. Okay, so now if you go to the electric field profile, so if you see now, so there is now the chosen is study 2 solution 1 data set. Okay, so you have to change this data set to parametric solution data set. Now there are parameter p and eigenfrequency as well. So if you go to the parametric value p, you can choose whatever parameter you want to see. For example, if 2 micron, then if you see these are the eigenfrequency corresponding to the parametric value p is equal to 2 micron. And if you go to the p equal to 3, so these are the parametric these are the solution corresponding to this the periodicity p equal to 3. And then if you want to change the eigenfrequencies, you can see. Okay, the electric field or eigenfrequency will change, or some q factor will also change, because now the periodicity is higher. So, and you still giving this eigenfrequency near 1.5 micron, and your periodicity is greater than your searching wavelength. So maybe this is sub means number of eigenfrequencies will be higher actually in this case. Okay, so this is the way to simulate the eigenfrequencies of your metasurface. Then in the next step, how to calculate the transition in this for the same. Anybody is asking some question? Okay, so for the transition, usually you can choose. Okay, so you can also divide your model something like this is EWFT. You can choose the second physics. I will choose the physics, one more physics, the same electromagnetic wave frequency domain. Now you can see EWFT2 is coming. Okay, so for this I will just rename for trans for my purpose. And then again, like everything, like periodic boundary condition will be the same. Okay, so I will just duplicate and then keep it here. And but the one additional piece, now we also need the source, because all the transition and scattering matrix comes when you solve the Maxwell equation with the source. So for that purpose, there are many type of source available in this one. For the specific, like if you ask me about dipole, so you can go point and then you put electric dipole as well, magnetic dipole as well, and then layered impedance. So but mostly for the metasurface purpose we use port source. So in the port source, if you put this port source here, now you have to define the boundary where this port should come, the light is coming from. So again I will go to the transparency section. So if you put from the top, so this port is selecting, because above the PML you cannot select. So at the end of PML you are selecting here. So if you select there, you can see this arrow is coming upward, but you want to excite from the downward. Okay, so the first thing you should choose the periodic boundary conditions, then port. This port should be periodic for this case, but you have different type of port: circular, coaxial, rectangular, numeric. So when you do boundary mode analysis, this numeric port is very beneficial, and especially for waveguide simulations and all these things. And then rectangular port, coaxial or circular, all these port is mostly used in excite the fiber. Like if fiber has a circular thing, then you can excite as a coaxial port, something like that. So but mostly in the metasurface we use periodic ports, and in the periodic ports you should have wave excitation at this port is on, and at the other port it should be off as well. Then this is the excitation port, and then also you should on the slit condition, because you are not putting your port at the top, it is in between your domain, right? That's why you should have active slit condition in this one. And then also at this, like if you imagine your metasurface,
What is slit condition?
I'm not exactly remember what is the slit condition, but if you have the port at some interior boundary, so this is the interior boundary inside the domain. Okay, the top one is this one, then you should on, otherwise it will give some errors.
Okay.
Okay, so this PEC backed, and then you can select the domain backed, because you are considering this light is coming from the uh, back from the domain, not from the PC means PC surface, right? So this is just PC backed or domain backed. I usually use domain backed. PC backed is something like if there is a PC boundary condition, perfect electric conductor at this boundary where the port is attached, then you can choose PC backed. But here this port is at the domain, so this is as a domain back, so it is something like light is coming from the back from the domain. So then you should choose the polarization of your port, so you can put something like X polarized light or bipolarized, anything you can put. Okay, and then if you want to give some incidence angle, you can put this angle as well. And if you want to move azimuthal angle, elevation angle is something like, so you can find this diagram according to this alpha and alpha 1 alpha 2 is there. So for example, if you are this at this point, so this point, this is your a1 vector and this is your a2 vector in your lattice, in the terms of lattice vector, then your x to gamma is something like that, and x to m is something like somewhere, along this line. So if you want to your kf vector along that one, then you can give some alpha 2 value, otherwise alpha 1 alpha 2 is 0. And then if you choose some alpha 1 angle, then it is alpha 1 is angle from your normal incidence. Okay, and then one more important thing, it is also asked background near the your port, like from actually this port is in the air, so this refractive index is n, and at the bottom there will be your substrate, then you should change this value to here. But I want to inform also that this is version 6.2, but if you go later version 6.3 or 6.4, then it is not required, because there is one option, it will take the refractive index from the background refractive index. But in this version, till this version, you have to choose this refractive index of your surrounding of the port. Then the second port, you will put you will also put the second port. I will just duplicate, and then I remove this port from here and I put this port here, and then this port should be off, because this is just a listening port, whatever coming light here and coming to here. But again, the light is going to the downward, not the upward as this arrow shows. So you have to toggle this power flow of this arrow. Now you can see port 1 is this one, light is coming on your meter surface. Then at port 2 the light is going out from this boundary. Okay, then your transition will be calculated like that. So this is the port condition, and now I will also define some variables to show you, like if you want to. Okay, so this is some other variable. You can also create variable tools, and just for then the integration also, I will choose one integration, not integration, just average value, and average over a boundary, and 6 will work. Okay, the 6 work. And also one more duplicate. So this is just to show you the how we can put the parameters 6 and 9, I think. Okay. Okay, so this is the top surface, and this average I am taking on the bottom surface. Okay, and yeah, one more thing. This at the periodic port, the output input power is 1 watt. Okay, so this is in the power. If you want to give electric field as 1, then you have to give the formula relation between E field and power. Okay, that is also square root or something of times electric field. So now I can define the variable, that is a transmission. Transition is something like average, sorry, so I have defined the average at top surface. Light is coming from that one, so this surface will work as a reflectance plane, and this plane work as a transition plane. So this ABOP1, so I will put AB bottom, and this will be ABH top. So the transition will be your AB bottom. So this will be average of your what it is called, pointing vector. Okay, so pointing vector will be your, I just, because I changed this trans as trans this model, so all things will called as a trans dot, and P so uh, pointing vector is defined as POAB. Okay, I will just search once. POABX. Okay. POAB. Transition along x-axis and divided by hmm, no. Actually, I am giving this 1 watt, right, power. So then it is coming here. So I have to multiply with the unit area to normalize it. And similarly, if I want to calculate reflection, then just yeah, just I have to change this average plane where I am taking. Okay, so this is just I put two formula to compare the reflectance and transmittance. And now next, once I set the port periodic boundary condition, then nothing else to. But now if you see here, I have taken two domain, okay, one transition and one is for EWFD for, then it is coming both here. So you have to tick only whatever physics you want to solve in this study. So I want to solve only transition, so not the eigenfrequency settings physics, okay. But if you are doing non-linear means simulation for non-linear for second harmonic or third harmonic, then actually these both is used in a combination with some combination, and then it will give you third harmonic or second harmonic simulation as well. So then in this step you just choose to the wavelength. So in this metasurface we already have eigenfrequency. So for example, quickly, the one mode is around 1.5 micron, right? So I will give values near that from 1.4 micron, and in a step of 2 nanometer till 1.6 micron. So it is 200 nanometer. Maybe I can give 5 micron for now, maybe, but you can reduce this. I have also one method where it is very fast sweeping in very fine way. I will tell you later. So for now you only need this thing. But if you are taking the study step as a frequency domain, this one, then only the change will be this wavelength domain. You have to give here in the terms of frequency, not in the terms of wavelength. That's it. So now if I put the compute, it may take some time, maybe 2 or 3 minutes, but let's see. So now you can see the progress here. 5 200 nanometer 5 yani. So
What are these different
Hmm? Progress.
these different things on the left side? Compute solution for parametric one.
Okay, so this compute is giving you the total progress. 64% is happening. Solution 5 maybe like this parametric one is because you are giving the sweep parametric value of wavelength, which is sweeping. So it is changing this wavelength. So that is the parametric. And then this linear solver and mumps is type of solver it is using actually.
Okay.
So instead of mumps, there is also different solver Parasido or Paradiso. I don't exactly remember. That is actually good in Mac, but in Windows mostly this mumps is coming. So if you are not selecting any particular solver, so by default it is according to your system it takes the base solver which can give the best speed in the simulation.
Okay.
But sometimes if you have comparison between the solver, I never studied about these things, but if you have some knowledge, then you can choose particular solver to solve your model.
Okay.
So now once this simulation is done, again you can see this electric field and reflectance, transient absorption and polarization curves is coming. But if you don't see this after computation, you can also create from Bundy plot. You can see here Bundy is something, this curve is happening. The same curve is happening in this one, reflectance. So this is actually Bundy plot basically. Then if you go to the global, it will give you directly all these parameters. You can see here actually there are I take the long range, that's why it is coming these two modes as well, and one mode is here as well. So then you can change the expression if you want transient, reflectance or both, or just absorption. You can just choose according to your things. And you can also choose from here. So now see domain 1 and domain 2. So frequency domain 2 is our transient model. So you can go and then you can go to the port, and inside the port there is R total, T total, RT total, A total, or some propagation constant, trans beta 1, beta 2 as well. And polarization states is also there, reflectance by order, reflectance by port, even S parameter and S parameter in dB, transition by port, transition by port name as well. So everything is here, whatever calculates, it calculates. And if you go to the global and in energy power also it is coming. But if you plot that variable as well, so I define this trans, right? Name trans, and if you plot, maybe it should come the same. Okay, maybe this formula I put, maybe something happens, otherwise it should come same the transition and that one. Maybe actually this is not the, because I am taking the, sorry, since I am taking the pointing vector, so it should come as a not x or y, it should come actually I think z component then. Yeah, so it is coming in the minus, maybe outward it is taking, so I should plot actually ABS of that one I think. Maybe I think something is mismatching, but otherwise this formula can work actually, electric field formula in the scattering model it works, because mostly I use that one only. So you can plot this transmission, you can use reflectance. Okay, So in this way, this metasurface simulation you can do. So we should stop here, and I will continue it on the group meeting day, the next tutorial. Okay.
Okay.
So
Thank you.
any question from audience? Is there any audience?
किया है
हाँ तो
अभी मतलब अभी मोटा मोटा तो सब समझ आ गया है फिर जब करेंगे मैं भी तब
हम्म,
अभी ऐसे तो समझ आ गया है जब फिर करके देखेंगे हो सकता है तब थोड़ा डाउट्स में
ओके। तो 4 ही लोग थे क्या अभी तक?
और भी थे, चले गए शायद वो।
शुरुआत में ज्यादा
ठीक
है लेकिन बीच
हाँ।
में जोड़ दिया होगा।
ठीक है। ओके।
ठीक है, थैंक यू वेरी मच
थैंक यू भैया
फॉर द
Thank you,
फुल
Divya.
टॉक।